Thank you very much, Mr. Chairman. It's almost good evening. I guess trying to follow up all the discussions about a very specific problem, district heating and cooling, which, as far as I know, it's very popular, and one of the things most of our fellow engineers are concerned, especially, Belgrade is probably very common. And somehow my topic was kind of like assigned to this session. So it may not be what you expected to conclude this very interesting session, but if you think about what I'm going to be talking the next few minutes, is all the design calculations we're doing for specific buildings and up to a block of buildings that may be making this issue a little bit more complex. There's a gap, and there's a difference, and that's what I'm going to be trying to address along with my colleagues here, as you notice, from the Institute of Environmental Research and Sustainable Development in Athens, Greece. We have been working within the frame of a European project on how to address this issue of what we actually observe in the field, measure, for example, and what we calculate, and how we can make this to come closer together. Well, it is a fact that we can measure everything. It is a fact that we can monitor everything in great detail. And especially when we're talking about buildings, this is a good area to apply all this need, because, as you see, buildings, a little bit over 40% here in Serbia, averaging about 35% in several other countries throughout Europe, and also across the Atlantic from the other side in the United States, and also a growing concern in China, where buildings are actually taking so much of our energy, whether that would be in any kind of fossil fuel or district heating or whatever, that we need to somehow figure out how we can balance. Well, as engineers, we do not panic. We can do it. We know how to do it. And of course, if you have applied all this technical know-how, all these methodologies that we can have to actually deploy your instrumentation in a building, measure everything, monitor everything, at the end of the day, what you realize, this is going to take time. This is a cumbersome process. Effort, time, money, we can do it. So, okay, well, if that's the case, for a single building, given that we have the time, given that we have the budget, we can do all these great things. But the complexity increases when we're talking about a pool of buildings, whether that would be at a municipality level. A large building owner may have thousands of buildings. A city, a country may have millions of buildings. How do we then handle this complexity of doing our calculations and actually coming close to what the reality, what we measure, what actually is being consumed in the building is all about? Now, one of the first things that comes to mind is, okay, it depends on how good your calculation software tool is. So there are methodologies, standardized approaches in terms of really figuring out that your calculation tool is accurate enough. There's also technical advice. One of the authoritative sources are the ASRI standard and the ASRI guideline that actually give us the knowledge of how to monitor, how to measure everything. So we have good guidance, but at the end of the day, there are still deviations, differences. Call them error from reality. Is it the calculation unable, not appropriate to deal with all this complexity? Not necessarily. The tools that we have in our days are very accurate. It's mathematics. complex reality in the buildings, complex tools can handle this physical phenomena, thermodynamics, the heat transfer in great detail, but it all depends on how much information we can provide as input, how accurate we are in describing what's actually happening in the building and the thousands and the millions of the buildings. So, in terms of handling this complexity and putting what is most essential, the human being inside the building, this unknown factor, us, whether we are at home, whether we are at the office working, how we interact with the building and how we are, most of the times, the determinant parameter in terms of how the building is performing. It is, if you think about it, like a car. You get a very efficient car, but depending on how you drive it, how aggressive you are, shifting gears, driving the car, or the driving conditions, whether you're on the highway or in the city. The same car would consume different amounts of gas, will have different mileage. So the same thing is happening with the buildings, but it is a fact, known that it is complex. So one of the ways of approaching this is to define typologies of buildings, group of buildings that are representative. Now, if we have some architects here, this would be maybe sometimes called an offensive statement, meaning that no, every building is unique. True, every building is unique, but making some kind of a compromise to solve the complexity, we want to characterize what we call a typical, an archetype, an example building to represent the millions of other similar buildings. This idea actually moves us from the unique building to the pool of millions of buildings that can be addressed in this way. Basic parameters to organize this approach is the size of the building, is the age of construction of the building, different construction periods, different building codes, different energy thermal behavior through the envelope or the installations and so forth, and climate. So the basic parameters, if we organize our building stock, and that has already been done for 20 national typos, 20 European countries, including Serbia, in a European project that I've indicated called EPISCOPE. We use now these types of buildings in order to address the complexity of our problem. But at the end of the day, what we have known, and these are examples from different studies that have been confirmed, to collect data from calculations and to collect data from actual energy consumption. What do we see here? We see a cloud of data. We don't see every point is an actual calculation and an actual energy consumption from a building. If we were to be on the 45-degree line, here we see the calculated, I was afraid of that, so it's difficult, but if you see this 45-degree line, if it was an ideal world, every point would be on that 45-degree line. The calculated is equal to the actual energy consumption. Perfect score. It doesn't happen. So there is a deviation, and you see from whether you look at this data from in Sweden, in Germany, there is a scatter. And this scatter can actually show us a result of the actual energy consumption being less than the calculated, as we see here on the right-hand side, or actually a lot of data where the actual is more than the calculated. And the same thing happens not only for residential buildings, but also for non-residential buildings on the lower hand, and actually for what we consider good design buildings. You've heard about the LEED buildings, the rating system. Look at this graph on the lower end, where you have the different LEED certified buildings, either silver or gold platinum. What do you observe? For the same rating, you have different values of the actual energy used. So for the same labeled building, the same category, at the end of the day, what you can have is a building that's consuming significantly different amounts of energy. Why is that? Because, for example, this rating system does not only look at the energy use, so depending on how well in your design and your installation of equipment and what you did with the building, you may have given different weight, different amount of emphasis on the energy aspects, and the end result is you will be consuming significantly different from other buildings in the same category. What would be the impact of that? Here's kind of like showing in a simple graphical form what could happen between your calculations, whether different design options, what you will install in terms of the envelope, in terms of the equipment, heating, cooling, and so forth, at your initial design or at your design at the end. Or if you're talking about energy refurbishment, retrofitting the building, before and after, you do your calculations, and what your actual results may show is something that would deviate. What we came to name and actually call this deviations, if your actual energy use is below what you calculated, this is called pre-bound. It's the opposite of the rebound, meaning that what I actually consume will be over my calculated value. So the rebound means I go higher from what I've calculated. The pre-bound would actually consume less than what I calculated. This is what the figures previously were showing us from different studies around Europe. So what we did was to look, in our case, in Greece. So we collected data from the energy performance certificates. As the implementation of APPD in Greece is occurring, we collect and we have this valuable amount of information from the energy performance certificates. Some of them, not all of them because it's not mandatory, has actual energy consumption data in the certificate. So we collected this, and this is how it looks like. And what we're looking here are residential buildings, and we split them. This is all the data. We split them, though, in the two regression lines, as you observe there, the orange and the purple, in multifamily apartment buildings and houses, two distinct types of the typology that I talked before. And what you look at and what you see here is what we call the pre-bound effect area, values where they're over the 45-degree line, where the actual, which is on the y-axis, is more than what we calculated. Where is that occurring most? It's actually occurring at the high energy performing buildings where the calculated energy use is low. So when we have low calculated energy use, we have this profound rebound effect. We can't estimate we'll actually consume more than what we predicted. When you have a low energy performing home, which means you calculate, this is an old home, no thermal insulation, old installations, I predict that will consume more. What happens? The actual is less. This is the area of the pre-bound effect, where the calculation is profoundly lower, the actual is profoundly lower than the calculated. So we are below the 45-degree line. What we're trying to do is collect and organize and analyze this data in groups in these typologies that I've talked before, in the organized manner of the single family, multifamily, in the different locations in the country and the different construction periods, and analyze the data and define a ratio of the actual over the calculated in these thousands of buildings to reflect an average condition of how close I am to reality. In the ideal world, you would have these adaptation factors being unity. What happens actually, depending on whether you look at the raw data or you look at a little bit screening the data, doing some data quality, but you see profoundly we are actually consuming much less than calculating, whether we're talking about the single family buildings or the multi-family apartment buildings, different ratios because there are different characteristics. Looking at the size of the bubbles, showing all the data. What you may notice, the size of the bubble shows the population, how much data we have. As you see, the database right now is dominated by multifamily apartments, buildings. The purple bubbles are small, which means the houses that we have for the different types are rather small. So there is a bias right now in the approach that we do not have enough houses with enough knowledge data, but it's the concept we're trying to approach. Another thing that we try to do is through some targeted field surveys. We're trying to figure out and listen to what the people are actually doing in terms of 3 specific parameters operating and heating their houses. First of all, how many hours do you actually heat your house? The calculation methodologies usually specify a certain amount of time. In our case, it is 18 hours per day. When we do a calculation, thermal load and thermal consumption calculation in Greece, we assume, it's in the methodology, most of the time standards tell you to do so, that it will be operated for 18 hours a day if it's a residential, if it is a house. So what is actually happening is people are using it for less. So automatically, you have a deviation, or part of this deviation being explained, that if I heat my house for less time, that would mean that I would consume less. And here you see the S-curves of this distribution. The shaded area shows the standard approach of saying 18 hours per day, and that's only about 5 to 8% of the buildings are actually operating as the standard implies. The second thing we will do in our homes is adjust the thermostat. The standard calculation says 20 degrees throughout the 18 hours to be in thermal comfort. But if I want to be in thermal comfort at home, or because of the energy cost, I will lower the thermostat. So that's another reaction we will do. And the other third one is I would not heat the entire house. I would switch, maybe turn off my central heating and use some other modes of local heating in specific rooms of my house where I am. I am in the living room, I'm in the bedroom, that's the part of the house that I heat. The calculations are being done for the entire floor, heated floor area of the building. So these are the 3 different, distinct, different occupant behaviors that would impact my calculations from the actual energy use. Again, defining this adaptation factor of the actual and the calculated, you see at the bottom how much that would impact, or how that could be taken into account to correct the calculations. These corrections, by no means we're trying to judge on the approach. It could be any approach, it could be any method, it could be your national tool that you're using. What we're trying to do is, given the methodology, given and knowing the end result, how can I bring the 2 together? Not for a single building, but for millions of buildings that I'm trying to approach this. And the overall methodology that has been followed in these 20 countries, European countries, among which is actually Serbia, I'll give you some information later on about this, has the overall approach of where we start from the typical buildings, the examples, use a calculation engine that in our case we have one of the national calculation methodologies in order to do the energy calculations. You have your own, so the concept doesn't really matter here. It's more of the approach. And from the typical buildings, with my calculation tool, I can really project the results, correcting with the adaptation factors that I defined, to the entire building stock. And once I have done that, I can start to look into the future with refurbishment rates, new construction rates, demolitions, what's actually happening to these millions of buildings, and project this in the end results. The outputs of this exercise gave us some confidence that we were approaching this problem, complex problem, with a relative accuracy. What's important to look here is that we tried different scenarios. What can we do to the building envelopes of all our buildings? What we can do to our systems, And the end result, without going into the details, is not one path will get us where we want to be in terms of meeting the goals and objectives at a national level, or as a building owner, if you have a large building stock, of really prioritizing what I need to do for my type of buildings that I'm trying to maintain. One approach will not get you there to meet aggressive targets, meaning I will change windows, meaning I would add thermal insulation, meaning I will change boilers. It's a combination of all this, reducing loads from the building envelope, actually upgrading to more energy efficient buildings that would manage to get us, as we looked here at the combined scenarios, that would manage to get us to the different goals that we have on a national basis, either energy conservation or CO2 emissions. And what I was referring to, the confidence, is that the results from the different corrections that we had for the adaptation factors, correcting and adapting our calculations, are the first 3 bars, where they're actually showing both the red, the energy, and the blue, the CO2 emissions. Whether we have used the different adaptation factors, trying to really bracket the solution. The solution is what comes with the solid bars, as you see, from the official statistics. We didn't influence that. That was data information that we get from the national statistics. So our estimates on the left show that we have managed to bracket the actual energy use and CO2 emissions we get from our census data for all the buildings in Greece, and that gave us some insight. We got it. We actually managed to capture this dropping trend or this actual behavior in the entire building stock. So it seems that the approach is working. I already promised you that this concept, this model that I presented for Greece, is already being worked out also in national level in Serbia. It was the University of Belgrade participating in this. So the concept of this approach, if it sounded interesting, it has already been developed. If you're interested in doing some kind of work, some other countries, I told you there are 20 of them that have already participated in this concept. And if you go online to this website, you can reach out and learn some more information. If you're the reading type, if you're after reading articles, a whole series of articles has been grouped together in a recent volume, just in November, published in Energy and Buildings, dedicated on this project, Episcope, on this idea, on this typology, and gives you examples of how you can actually handle and treat this gap, this difference of calculation to actual energy performance. As I said, not for one building, but for millions or thousands, millions of buildings in the large scales. So this approach, it has a name. It's called bottom-up because we start from the bottom and we raise to the big picture. Seems to be working. It has complexity. It's not straightforward. It seems an approach where we can apply the concept and periodically, of course, upgrade using a balance of census data, statistics, and some short surveys. The underlying, what we already had a hunch that this is actually happening, is occupancy. Us, the occupants, play a determinant role. So in addition to thermal insulation, in addition to thermal efficiency, COP, higher performing new systems and so forth, we need to also interact with the users, understand how they behave in the building in order to be able to have the desirable end effect. If we use this concept of the adaptation factors, it seems that we can actually manage to follow an approach that can be repeated, can be upgraded to handle this complexity, as I said, for millions of buildings. And finally, what we're trying to do is to be able, whether we're talking to a government or a community or a large building owner that is interested of how to handle this thousands of buildings that he owns, is to make good estimates, to make good predictions of different energy conservation measures and be able to come close to what realistically is going to happen. And of course, in terms of policies, as you're doing here, I know in Serbia, as we're doing throughout Europe, is to be able to look at 2020, 2030 and be able to really put down policies that would have effective results on a large scale. Some bibliography for you if you're interested to go through. And Mr. Chairman, thank you very much for your patience and for all of you for listening to this presentation. I hope there were some interesting elements there for you. Thank you very much.
Thank you very much, Mr. Balaras. Very interesting paper. We also deal with similar questions, occupants' behavior, raising of awareness of possibility of savings. Just to clarify a lot of data, just a few words, how did you gather that data? What kind of measurement, and is it
the main data comes from the Energy Performance Certificate Registry. It's a central registry that automatically in Greece, every time you issue an EPC, it goes into that database. The data progressively reflects our entire building stock. Right now we are close to 1 million EPCs. Part of them, a small sample, as I showed you, about 1,800 of them contain actual energy use which comes from energy bills. So it has the electricity, it has the oil, or it has the natural gas or whatever. So that's where we reach out and pull out this information. Additionally, what we have tried, but I didn't present it here because it was on a limited basis, we tried a field survey. We went out to buildings where they had actual implementation of energy conservation measures, and we collected the energy bills before and the energy bills after. This is not easy to do. So our limited campaign actually reached out to 80 dwellings. Not bad, but we obtained similar results. So it seems, and there it's more difficult because there you have specific type of a building with a specific application in terms of, I'm changing my windows, what's going to happen actually? I'm changing my boiler, what's going to happen actually? You need a lot of variety, different combinations to actually fill in the matrix. The matrix being the typology. Different types of buildings, different ages, different locations. So that exercise, again, it kind of like tried to prove the concept. Monitoring will, if we ever get to smart buildings, to smart metering, we can get automatically electricity. Somehow we could do something similar for natural gas. It's very difficult, and that's, I don't even know how to handle if you're burning oil. Which is something, for example, very common in Greece. We're burning heating oil, which you don't monitor of where it's coming from, other than bills. So, and that you depend on the owner having, not just 1 year, 3 years average, that's the approach of this kind of information. Not easy to do, but it seems that overall approach, at least with the certificates, works out.
Thank you very much. Da li ima neko još pitanje za gospodina Balarasa? Izvolite.
Then I will ask one question. Actually, I wrote down 3, but as your presentation went out, you answered for the first 3. So let's say, I would just like to clarify one question. So you extract some kind of coefficient of performance, which means 0.91, 0.8, I wrote it down. So have you included in the EPISCAP in proposals for refurbishment of buildings, or how do you use those coefficients?
Okay, well, these coefficients are not just one. I presented an average for houses, an average for apartment buildings. That coefficient actually goes inside and have reported these values in the paper. So you have for different types. If it is a house located in the north part of Greece, constructed before 1980, that's one type, has a different correction factor from another house somewhere else in the country, some other construction period. So you have this matrix where you're actually trying to develop the different adaptation factors that most closely resemble and reflect the actual condition, and taking this now into the big process that we do for the building stock analysis, is once we do the analysis and we calculate energy conservation measures, the effectiveness using our standard methodology, before we look at the result, we adapt the calculation. And then we take this as being the predicted actual energy use for our typical building, and we multiply this with the floor area for so many million square meters of houses in Greece are this type. So at the end you have the contribution for this family of houses constructed before 1980 in the north part of Greece would have so much energy, which is an actual consumption, and that is then transformed to CO2 emissions, which has already been adapted to being closer than an estimate that we know, and we looked at the actual predictions and the statistics, the official statistics, that there's a big gap. How can I close this gap is part of this effort, to come closer to really making estimates either of the existing condition or the result of energy conservation measures, which for a building owner that I don't have millions of buildings, I have 1,000. For example, apartment buildings that I manage, it's something similar importance in order to be able to come close with something realistic. It's not that the calculations are wrong, we just do not have all the information for the 1,000 or millions of buildings to precisely be able to simulate their performance, in addition to the user and the occupant role.
Thank you very much.
Thank you. Any more questions? So, once again, thank you very much, Mr. Balaras.